In example 5 from the chapter on mechanical systems, we're posed with a problem which is made up of a rack and pinion system that's shown. We have a gear which is pinned to ground at O. It's in gear contact with the rack at B. A is connected back to B with a spring of stiffness K and damper of a damping coefficient of C. The gear contact between the gear and the rack simply means that the gear doesn't slip on the rack as it moves. So let's start out our process here on deriving our equations of motion. So we'll draw our FBDs. If we look at the gear, well, the gear is pinned to ground, so there needs to be some forces here at the bearings to hold it in place. We might put in some weight forces along the way, but we'll find that we don't really need those. We have some normal forces holding up A and B. Again, those will not be important, but for completeness, let's put those in. There's a torque of T, which is acting on the gear. Between the gear and the rack, in order to maintain that no slip, there has to be a contact force. So what I'll do is arbitrarily draw the contact force on the gear to the left. During half the cycle it's going to be to the left and the other half to the right. So we just choose one. But once we have that set, then we have to draw the force on the rack in the opposite way as that. We have the spring force and the dashpot force on A. Recall that the force in the spring is K times the relative stretch in the spring. So we need a variable here to describe the motion of the rack B. With that, we know that we can write the force then as K times, let's say, X minus Y. If we write it down as that, when X is larger than Y, the spring is stretched, so it's going to be pulling back to the left. Same way with the dashpot force. If we write this as C times X dot minus Y dot, then the dashpot force is pulling back to the left whenever X dot's larger than Y dot. And then from Newton's third law, we have an equal and opposite force, or set of forces, on B. I think that's it. So now let's write down our Newton-Euler equations. So for the gear, let's write down a moment equation. Let's write down a moment equation about point O. Well, with the sign convention of theta that's shown, that's positive in the counterclockwise sense, we have T as being plus, the contact force F, and I failed to write down the radius of the gear, so let's call that R. It's going to be F times R. It's in a clockwise, so that's a minus sign, and that's the only two things causing a moment, so therefore that's equal to I theta double dot. From there. So from this, I'm going to say that F, the contact force, is equal to T minus the mass moment of inertia about O theta double dot divided by R. Let's look at the rack B. Y I define as being positive to the right, so when I sum the forces, then F is plus. The spring force is plus K minus, or K times X minus Y. The dashpot force is plus X dot minus Y dot times C. And that's that. And so the mass of B is given as 2m times, therefore, Y double dot. So if I substitute the gear equation into the rack equation, what I have here is a T minus I theta double dot divided by R. That's F. We have K X minus Y plus C X dot minus Y dot, like that. and that's equal to 2my double dot. So that's one equation we got from combining those two. And lastly, we have a force equation for A. If I sum forces on A in x is positive to the right, so that's a minus k x minus y minus c x dot minus y dot, and that's equal to ma, so that's m times x double dot. So right now we have two differential equations. How many do we need? So let's first determine the number of degrees of freedom. If we look back at the problem, it looks like we got three bodies, the gear, the rack, and A. One might think that one would need three coordinates to describe the motion of those, but in fact that's not quite true. We only have 2 degrees of freedom. How do we know that? Well, if we go through our check here and say let's suppose we fix the rotation of the gear, can we move y and x? Well, the answer is no. We can move x, but we can't move y because y is constrained to no slip with the gear. Hold y fixed, you can't change theta, although you can change x. If you hold x fixed, you cannot independently change y and theta. So in the end, our thought process here says we have 2 degrees of freedom. What this means is that in the end we need 2 equations of motion. We have 2, but we have 3 variables, theta, x, and y. So we now need to come up with the constraint that exists between theta and y. O here is a fixed point. Theta was defined positively like that, so I would write the contact point C as having a velocity, a speed here of r theta dot. So that's coming so simply from the fact the gear is rotating about O. But the no slip between the gear and rack B says that the velocity of C on the gear is the same as the velocity of C on B. So therefore the velocity of B is written as y dot. What this says is that the change in position y is equal to r times the change in rotation for the gear. Y dot, as we just saw, was r theta dot. We take one more time derivative of that, and we get r theta double dot. So these are the 3 things we're going to need to substitute back into our equations of motion. So let's do that. So we have T minus I theta double dot divided by R plus K x minus ky, y was r theta. We have cx dot minus cy dot, that's c r theta dot, is equal to 2 m y double dot, that's r theta double dot, like that. Our second equation is what mx double dot. I'm going to bring the damping and stiffness terms over here to the same side. So it's going to be a plus kx. There's going to be a minus ky, which is r theta. I have a cx dot. I have a minus cy dot, so that's cr theta dot, like that. And we have that as such. I'm going to put all of the theta and x terms on one side. So the first equation gives us a 2 mr theta double dot, like that. Oops, I need to not close my brackets yet because I've got another term. So I've got 2 mr plus I over r theta double dot. Then I'm going to have a term here of c times r theta dot. I'm going to have a minus c x dot. I'm going to have a k r theta. I will have a minus c, oops, already got that one down. I'm going to have a minus kx, like that. And that's going to be equal to the torque on the gear T. Second equation, mx double dot, the damping term minus cr theta dot plus cx dot. I have a minus kr theta plus kx, like that, and that's equal to a 0 as that. Okay, so let's say I want to put this in matrix form. In matrix form, the mass matrix is going to be 2 mr plus I over r in the 1, 1 position. I have a 0 and a 0 there. I have an m here. Theta double dot, x double dot. The stiffness or the damping terms are going to be CR minus C minus CR times C times what? Theta dot x dot. The stiffness terms are going to be, what do we have? K times R minus K minus KR K, like that. And the theta x like this. And on the right hand side I have the input terms. Well, I need to make one correction here. If you go back to this equation, you see there's a 1 over r times a t. So there needs to be a 1 over r there multiplying that t. So the first equation is going to have an inhomogeneous term of t over r, like that, and a 0 as that. So this is the matrix vector form.